Hi everyone, it's Mr. H here, and welcome to this lesson on the photoelectric effect, one of the breakthrough effects in quantization of energy. It's important we have a good grounding in this story so far so we understand what's happening today. In the 1800s, it was understood that higher frequency waves have a higher energy. Our understanding today of that hasn't changed. We understand that, and that's true. However, the ultraviolet catastrophe was the big problem, and that asked, if ultraviolet waves have a higher energy, why don't we have tons of energy emitted from ultraviolet radiation from black bodies? Well, in 1901, Planck came along and he said that energy was actually quantized. And what he proposed is that anytime we have a black body is heated up, it's going to have the vibration of the molecules inside, or of the atoms inside that black body. Well, he said it has to be at quantized values. And so he said that n can be 1, 2, 3, 4, but it can't be decimal values. And so rearranging that equation and setting n to be equal to 1, he said the maximum possible frequency was this equation right here, the energy of a vibration divided by Planck's constant. So frequency of most radiation within the ultraviolet spectrum is non-existent. This vibrational energy is actually energy between energy levels in an atom. What we now know is that when let's say you have an electron, if you give it more energy, it's going to jump to a next energy level. Can't jump to something in between that level and the one above it. It has quantized energy levels. And so electrons have these quantized energy levels. Energy, therefore, is quantized. So what scientists began doing is shining light at certain metals. Sodium was a prime example of, because sodium is technically a metal, it's a prime example of something that they would shine light at. And what they found is as they emitted photons, particularly as they approached a certain end of the spectrum, then more electrons were released from that material. Quite remarkable that light can emit an electron. But think about it this way. It's just really a collision between two particles. I know a photon isn't a mass, but just think about it in terms of that classical definition of physics. In terms of the conservation of energy, we can see that the energy from a photon is equal to the energy to free that electron plus the energy that gets it moving, the kinetic energy that it has. And so this is often written as E photon this is called the work function, the energy to free the electron, plus the energy of the photoelectron, or sometimes referred to as EK of the electron, the kinetic energy of the electron. So what happened is about 15 years before Planck's discovery of quantization of energy, Hertz was doing an experiment where he set up this idea of the photoelectric effect, but he set up a full circuit like this. And so as he shone light on this surface, sodium, copper, something like that, some type of metal surface, he was able to release electrons from that surface, and they would hit the opposite surface, and then what would happen is a current would be induced in this coil of wire that had this big gap in between. So with this knowledge, let's see if you can predict what's going to happen and why. So there's going to be two parts to this photoelectric effect predict, observe, explain that I'm going to ask you. The first part is this. What wavelengths of light will cause electrons to be emitted? Will they be the ultraviolet? Will they be something in between? Will they be the infrared? Remember, infrared is larger wavelengths. Ultraviolet is shorter wavelengths. And then we have the visible spectrum between those. And so that's your prediction that you should make here. All wavelengths will emit electrons, just the highest wavelengths, just the lowest wavelengths, or something else entirely. So I'm using this PhET interactive photoelectric effect demo, and what you can see is right now it's set to the infrared side of the spectrum, so long wavelengths. My intensity is fully turned up, so it's a very intense light. You can see I can turn the intensity down and up, and it just gets darker, meaning that it's more intense light being shone on it. As I take that infrared light and I move closer to the ultraviolet end of the spectrum, now we begin to see electrons released. Well, what can you conclude? Well, we have shorter wavelengths. Clearly shorter wavelengths are releasing the electrons, meaning higher frequencies. So the highest frequencies and lowest wavelengths were the correct answer for that part. Well, why is that the case? Well, it's because the light beam needs a minimum frequency, it's called the threshold frequency, sometimes the cutoff frequency, to release electrons. The universal wave equation for light, if you remember, V equals frequency times wavelength, and in terms of light, that is the speed of light, so it's c. And so the shorter the wavelength, the greater the frequency. Simply rearranging that equation, they're inversely proportional to each other, so that's how we can find that. Electrons must be given enough energy to break free from their atom. This is done by using a high frequency. Since the energy of a photon is equal to h, which is very, very small, we need a very high frequency. So the second thing I want to ask you is this. Does increasing the intensity of light change the speed that electrons are emitted at? No change in speed. Does higher intensity light mean a higher speed, or does higher intensity light mean a lower speed? So let's go back to that and see how this works. So right now I have the intensity set to 100%, and I have, you can see from the ultraviolet light that's being shone on the sodium, that there is a lot of electrons. There are a lot of electrons coming off of that sodium. And then you can see that that's inducing a current in the circuit that we are forming that way. If I turn the intensity down, let's see what happens to the speed of these electrons that are being released. Is that going to change? I turn that intensity down. You can see that fewer electrons are being emitted, but are they moving any slower? No. They're moving at about the same speed on average that they were moving when the intensity was higher. Let's just go back up. I'm going to increase the intensity again here. And so you see those electrons aren't moving faster overall, right? Obviously they're starting off slow and they're moving faster as they hit this other plate. But the average speed that they move across here hasn't changed as I change the intensity. So we can see that we found no change in speed. Well, why was that? Why when we change the intensity did they not get faster and faster and faster? Well, it's because when a photon strikes a metal surface, all the energy of that photon is absorbed by one electron in one event. Remember the analogy I had earlier of just thinking about a photon hitting an electron, right? If you increase the light intensity, you increase the number of these events, hence more electrons are emitted, but not the speed. We obviously saw more electrons emitted as the intensity went up, and less electrons as the intensity went down, but no change in the average speed of those electrons. Since the energy of a photon depends on the frequency of the light, remember the energy of the photon, as found by Planck, was equal to Planck's constant times the frequency of the light. The only way to change the speed of electrons is to change the frequency of the light. So if I turned up the frequency, I would have had the electrons actually go faster. So let's actually see how this works. I'm in the visible part of the spectrum. I'm going to move now closer to the ultraviolet light side of the spectrum. Let's see if the speed of these particles actually increases. So here we go. As I go closer and closer, you can clearly see that those particles that are being released are released and they get faster and faster. And that's what happens. Not that we get more intensity changing the speed, but that we get a higher frequency changing the speed. This is a breakthrough. There's so many applications of this that we can use, and one of the basic things we can calculate is the speed of that electron that gets emitted. And so, as we noted earlier, the energy of the photon is given to free the electron. So it actually has to release the electron from its hold by the atom itself, by the nucleus. And then it also has to be converted into energy that's going to move the electron, this kinetic energy. And so we use the energy of the photon, and then the energy to free the electron is called the work function, W naught. And then the moving the electron is EK of the electron, or EK of the photoelectron. It's not like it's a special electron. We just call it a photoelectron because it's been released by a photon. Now we also know that the energy of a photon is Planck's constant times the frequency of that light. And then rearranging that equation, we get the kinetic energy of the photoelectron is equal to Planck's constant times the frequency of the light minus the work function, the amount of energy needed to free the electron. So here we put it all together. The kinetic energy of a released electron is equal to the energy of a photon, there's the energy of the photon, minus the energy the electron needs to break free, this work function. H is Planck's constant, 6.63 times 10 to the negative 34 joule seconds. The EK of the electron is the maximum kinetic energy of the photoelectron. If there was water or air or something like that, and not quite a vacuum, it wouldn't quite reach that maximum kinetic energy. We're going to assume it's always in a vacuum. F is the frequency of the electromagnetic radiation on electrons, so it's the frequency of the light. And W naught is the work function of the metal. It's the energy required to break free in joules. Now, sometimes you're going to be given things in electron volts, particularly the work function. If that's the case, we know that 1 electron volt from previously in our course is 1.602 times 10 to the negative 19 joules. So if we want the work function in joules in order to do our calculation, because we have the kinetic energy as joules, and then H times F would give us in joules, what we would have to do is we would have to multiply the work function in electron volts by that ratio so that the electron volts cancels out with electron volts and we're left with units of joules. So let's actually do a question together and see how this works. Let's look at an example of the photoelectric effect. If a photoelectron of wavelength 452 nanometers hits metallic sodium, just like we saw in the FET demo a minute ago, sodium has a work function of 2.3 electron volts. What's the speed of the photoelectron produced? Well, what are we given? We're given the wavelength. We know the wavelength of this light is 452 nanometers, which is 452 times 10 to the negative 9 meters. We also are given the work function. We know that's W naught, but that's given in electron volts. And so an electron volts, we have the ratio of those to joules above. And so I'm going to put 1 electron volt in the denominator to cancel that out, and 1.602 times 10 to the negative 19 joules in the numerator. The electron volts are going to cancel out, and it turns out that I have a work function of 3.6846. I'm going to carry a couple extra sig digs, times 10 to the negative 19 joules. All right, anything else? Well, I also know Planck's constant. I have it written up above. There's one thing that we always are going to know, because if a photoelectron is being emitted, then we know that the mass of that electron is 9.11 times 10 to the negative 31 kilograms. Again, we've seen that previously in our course. It was a tremendous discovery made by Millikan in his oil drop experiment. Beyond that, we know also the speed of light. And we know that speed of light in air in a vacuum is 3.00 times 10 to the 8 meters per second. So keep in mind these two, they're important. They are not givens, but they are values that you should have access to, and they are available on your equation sheet as well. So let's go ahead and set up the equation and actually try to solve this. We know that the kinetic energy is equal to the energy required, or the energy it's going to be moving at, minus the work function, minus the energy required to release it. And because it's kinetic energy, we know kinetic energy is 1/2 mv squared. It's the kinetic energy of the electron. So I'm going to just write E for electron, of the mass of the electron, and E for the velocity of the electron. And I'm going to rearrange this because I'm trying to solve for VE. This is the value I'm trying to solve for right here. I'm going to rearrange this for that. So I'm going to multiply both sides by 2, divide both sides by the mass of the electron. That's going to cancel out. Take this side, multiply it by 2, divide by the mass of the electron. And what I'm going to be left with is VE is the square root of 2 over the mass of the electron times Planck's constant times the frequency minus W naught. Now you might think for a second, I don't know what the frequency is, and you'd be correct. So keep in mind that frequency comes from this equation. Frequency times wavelength is the speed. And so we can rearrange the frequency to be the speed divided by the wavelength. And I'm going to substitute that in here before I do this calculation. So 2 over the mass of the electron times h times c over lambda minus W naught. So I'm going to sub those numbers in now and get a final answer, and let's see if you find the same thing. So what you get is 4.0 times 10 to the 5 meters per second. Make sure you have a negative 31 as your kilograms, powers the power of 10 to the negative 34 as Planck's constant, 10 to the 8, 10 to the negative 9. You could have also written this as 4.52 times 10 to the negative 7. You could have also done the frequency calculation ahead of time, so you don't have to do that calculation right there if you don't want to. But you do have to calculate all of this right here before you subtract the work function times 10 to the negative 19 there. It gets to be a number a little bit smaller than 400,000, but to 2 sig digs it rounds to 4.0 times 10 to the 5, or 400,000 with 2 sig digs. So there you go. Hope that's helpful. And here we go, ready to find out more about quantum physics.